Hello, my name is Drishan, and today I'll be speaking about my digital assignment on computer organization and architecture. The assignment was submitted in Vellore Institute of Technology under the faculty Professor Dhanwal R. The first question is analysis of microprocessing element from any vendor of your choice based on the concepts learned in computer organization and architecture syllabus. My I selected the microprocessor at Mega V48, and as you can see there's a clear block diagram of the microprocessor AVR CPU. We are using AVR CPU with which has SRAM, flash, and AD converter. The oscillators with the this thing also the microprocessor also consists of debug wire, program logic, power supervision, PUR, BOD, and reset. It also consists of EEPR OM. The time to counter is 8-bit, 16-bit, 8-bit analog and SPI TWI. Okay, so out of this all elements of the microprocessing unit, the I have separately exhibited all the diagrams of every unit as given in the another question. Give internal diagram of each and every block. So this is the AVR architecture, the main CPU diagram. This is the status register, the AVR status register, which has read and write components. Okay, then we have CPU general purpose registers till R3131 registers. We have clock distribution diagram, crystal oscillation connections, external clock drive configuration, reset logic, watchdog timer, input and output pin equivalent schematic, general digital input output, alternate port functions, and also 8-bit timer clock block diagram. We also have counter unit block diagram, output compare unit block diagram, compare match, output unit schematic, T1 by T2 pin sampling, prescaler time counter and time counter 0 and time counter 1, 16-bit time counter block diagram, prescale, time timer and counter, SPI block diagram, SPI master and slave interconnection, USART block diagram, clock generation, logic block diagram, overview of TWI module, TWI address magic logic block diagram, data transfer in master and receiver mode, analog comparative block diagram, analog to digital converter block diagram, schematic operation, ADC, auto trigger logic, ADC prescaler. Okay, so the second question was provide the instruction set of the microprocessing element with the clock required, time and machine cycle required, memory flags affected, type of instruction based on the addressing modes operation. So basically the Atmega 48, 88 and 168 is a low power CMOS 8-bit microcontroller based on AVR enhanced architecture features. So we execute the powerful instruction in just one single clock cycle. This microprocessor basically achieves through approaching 1 MIPS per megahertz, allowing the system designer to optimize power consumption versus processing speed. Okay, so we have the instruction set right there. Every instruction set I have, which consists of add, subtract, ADD, convert, or, and every basic instruction, as well as multiplication, clear, set, INC, FMUL. We have branching instructions for loop. We have RM, RJMP, IJMP, JMP, then RET, etc. We have bit and bit test instructions. We have data transfer instruction and MCU instruction. The AVR core basically combines a rich instruction set of 32 general purpose working registers. All 32 registers are directly connected to the ALU, allowing the two independent registers to be accessed in one single instruction executed in one clock cycle. So therefore, the fast access register only contains 32-bit general purpose registers, 32 into 8-bit 32 8-bit general purpose registers, which with the clock cycle access time. This allows single cycle ALU operation. In a typical ALU operation, two operands are output from register, flash program memory, instruction register, instruction decoder, program counter, lines, general purpose ALU status, control input output lines, EPROM, SRAM, director addressing mode, type, etc. Six of the register can be used up as three 16-bit indirect register pointers for the data addressing, enabling efficient addresses calculations. One of these address pointer can also be used as address pointer for lookup tables in flash program memory. These added functions registers are 16-bit X, Y, Z register described in the later section. Okay, so the third question was explain the microprocessing unit of the microprocessing element of the architecture. So the main function of CPU is to core is to ensure the program execution. That is the main purpose of every microprocessor. The CPU must therefore be able to access memories, perform calculations, control peripherals, and handle interrupts. In order to maximize the performance and parallelism, the AVR uses Harvard structure to with separate memories and buses from program data instructions in the program memory are executed with a single level pipelining. So in typical ALU operation, two operands are basically output from the register file. The operation is executed and the result is stored back in the register file in one clock cycle. The ALU supports arithmetic and logic operation between registers or between a constant or a register. Program flow is provided by conditional and unconditional jump and call instruction, able to directly address the whole address space. Most AVR instructions have single 16-bit word format. Every program memory address contains a 16 to 32-bit instruction. Program flash memory is divided into two sections: the boot section of the program and the application section of the program. Alright. Boot sections have dedicated log bits to for write and reader line protection. The SPMU section that writes into application flash memory section must reside in the boot program section. Correlate the microprocessing unit, microprocessor, microcontroller, IP structure, architecture with the architecture discussed in module 1 and module 2. So basically, Harvard architecture is a part of the computer architecture that separates its memory into two parts of data and instructions that are stored separately. The architecture also has separate buses for data transfer and instruction that fetches. This allows the CPU to fetch data instruction at the same time. Address space, memory model, memory space, unified or single flat address space. Based on my understanding of ARM architecture was originally from von Neumann architecture, and even to this day, the process code retains its inherent attribute. Advances in technology allow the designers to employ a separate part of for instruction and data from a single memory space. Okay, so fifth question was elaborate the register organization of microprocessor element. First of all, we have status register. The status register contains information about the result of most recently executed arithmetic instruction. This information can be used for altering program flow in order to perform conditional operation. Note that the status register is updated after all ALU operation is specified in the instruction set reference. This will be in many cases remove the need for using dedicated compare instructions, resulting in faster and more compact code. The status register is not automatically stored when entering an interrupt routine and restored when returning from an interrupt. This must be handled by software. So we have bit 60, bit copy storage, bit 4s, sign bit equals to n or v. We have bit 3v, 2 complements overflow flag, bit 2 n negative flag, we have 0 flag, we have character. Then we come to general purpose register. The register is optimized for the AVR NHRISC instruction set. Most of the instructions operating on the register have direct access to all the register. In each register, data is also like assigned in data memory address, mapping them directly to the first 32 locations in the user data space. Although not physically implemented as SRAM locations, the memory organizations provide a great flexibility in access to the register as X, Y, and Z pointer registers can be set to index any register file. So we have the X register, Y register, and the Z register. The register R36 to R31 have some added function to the general purpose usage. These registers are 16-bit address pointers for indirect addressing of data space. The three indirect addresses register XYZ defined as these as shown in the figure. Yeah, we also have a stack pointer. Stack pointer is, as you know, the basically used to store stack. There is a separate data that we can decide in a particular memory, and we can call it stack. The data can be used to store programs or sorry, memory. The memory can be used to store programs and data. Note that the stack is implemented as growing from higher memory locations to lower memory locations. This implies that a stack push command decreases the stack pointer. Question number 6 was explain the type of algorithm used for signed and unsigned calculations, addition, multiplication, etc. So these are the code for multiplication and these are the code for addition. Question number 7 was find whatever control logic unit used and correlate its performance with the type of control unit in module 3 in our syllabus. Okay, so nested vector interrupt collector, the NVIC is closely integrated with the core to achieve the low latency interrupt features, including external interrupt configurable from 1 to 240. This configured at implementation configurable levels of interrupt priority from 82 to 56, dynamic reprioritization of interrupts, then priority grouping. This enables selection from preempting interrupts level and non-preempting interrupts level. Wake up interrupt controller. Okay, explaining queuing the memory management system, the processing element selected, and list. This is the eighth question. The device is manufactured using Atmel's high non-volatile memory technology on ISP flash allows the program to be reprogrammed in system through an SPI interface by a conventional non-volatile programmer by an on-chip boot program running in the AVR core. Each register is also assigned data memory address, mapping them directly into first 32 locations of user data space. Although not being physically implemented as SRAM locations, the memory organization provides great flexibility in access to registers. Okay, so elaborate the pipeline and parallel processing capabilities of the unit and hazard management. That in two clock cycles, instructions is of four-stage pipelines, and each stage needs two clock cycles. The integer pipeline is four stages, and the floating point pipeline is five stage. The pipeline diagram looks more like CISC instructions with different latencies. That is a pure RISC pipeline, hence the confusion. For example, the write store in the ALU pipe is not separate stage because writes are executed at the end of the execute stage. Same for the prefetch, it is only activated when predicting the branches, so it is not really a separate pipeline state. In normal program execution, instructions are fetched in order. Find whether the processor level parallelism is available in element selected. Illustrate the cache coherence and protocol used for handling memory. So the microprocessor contains a variety of inter-process communication IPC mechanism. Basically, these mechanisms can be used to exchange data and coordinate the activities of multiple asynchronous processes within a single memory system. Typically, the new processor immediately uses exec function to load a new program, but this microprocessor also supports the system function miss, which create the lightweight process. A process created with miss is shares some of its process state values with its parent process. Dispatch of lightweight process is done in the kernel and has the same overhead as any dispatching any process. A cache is a cache memory is a small, very fast memory that retains copies of free, recently used memory values. It usually implemented on the same chip as the processor. So that will be all today. If you if you want to see the research paper, then I will upload the link in the bio. Thank you very much.